Hey guys, welcome back to this channel. It is Abjoin Babatunde, popular for this channel named Episode Designer. You are welcome back to our videos. I think it has been a long time since we released video on this channel. We had a little challenge, but thank God we are continuing from where we stopped. I'm going to be making videos on petroleum refining, advanced petroleum refining. You can see from the topic. So this is like the starting video from the series, which is we are going to be using petroleum assay characterization method for petroleum refining to characterize petroleum crude oil, and we are going to be doing petroleum refining simulation in Aspen HYSYS. To get things started, the first thing, like we did in the previous video on the basis of petroleum characterization in Aspen HYSYS, we are going to be characterizing crudes and we are going to be blending them. So to characterize crudes with new advanced method in Aspen HYSYS, which is petroleum assay characterization method. You can see it in the navigation pin here. This is the petroleum assay. So you can choose different assay list in this listing, assay summary. So I'm going to be adding assay. So you can add assay from library, you can add from file, and you can manually enter. So I'm going to be doing these three. I'm going to be adding 3 assays, and I'm going to be using these 3 methods to add those assays so that you can learn from the process. And the first assay that I'm going to be adding is the Bonny Medium Nigerian crude. So this one is I'm going to be adding it from the library. So I'm going to say add from library. So you can easily get a list. It is like this. There is a lot of assays data installed with Aspen HYSYS through the Petroleum assay interface. So you can easily get a list of the assay here. So you can search the name of assay that you want. So I'm going to just search Bonny Light here. So I'm going to search Bonny Light, and okay. So you're going to sort Bonny Light. I think I didn't get. Okay, let me write it here. Going to do it automatic. Okay, this one is for filtering. So, but the way I okay, so I'm going to write Bonny Medium. So this is the acid I'm adding. So I'm going to pick it. So you can write. I've not finished the naming, so I'm just using this acid is from 1997 from Nigeria. So, and these are the data for the assay, like description. Although most of the data is in the interface to be added. So let's wait for it. So we have the Bonny Light data here. This is a cut sheet. This is the cut points of the distillation through boiling point distillation, and this is the properties of the cut sheet. You have the liquid density, the sulfur property, the paraffin and naphtins, and the freeze point, pour point, and the cloud point, and the kinematic viscosity data for the Bonny Medium assay. and you can see the pure component data, and you can see the distillation data. There's no distillation data, so but you can have the pure component data here. So so I'm going to go back to the interface again and add the second one from a file. Maybe like you download, there are some website that you can download assay data from, like ExxonMobil data website. From you can download a lot of assay data that you can use in your process and your simulation to test, you understand, or even in your research, you understand. So I'm going to choose different formats. This Aspen Tech you can even download from Aspen Tech website too, and all these company. So I'm using ExxonMobil because the assay that I want to add is in this form, is a Basra assay from Iraq, and you're having quoted this property. So it's going to change, you're going to transfer these properties to this data to Aspen HYSYS. So let me close this. So I just go to the page and click the file. So this is the file here. So the next thing is to import. So the file has been added to the case, and this is the simulation file here. So we have the data that is from the Excel sheet that is downloaded from the ExxonMobil website, and you have the pure components is not having any pure component data, and the distillation data for the crude oil, which is here. So I'm going to do the last one. Is that it's very simple to do, and this has been characterized. This still need to be characterized. That's why we are seeing the symbol like this. So the last one is manually entered. So I'm going to manually enter the last one based on the multi-cut properties. And to do the multi-cut, this is the assay that I want to add. Is this is the assay here. So you are going to be adding the cut properties here. Although you can use the other method like your stream, single stream. This one you can do the cut properties, but for the kind of because I have a lot of properties that I want to characterize with the assay in order to get the properties of the assay very well. So I'm going to be using multi-cut properties method. So I'm going to be adding number of cuts to be equal to the number of cuts that I have here. So I have like 12 cuts here, from cut 1 to 12, isn't it? Okay, this is 12 cuts. So I'm going to be adding 12 here. So let me use, so 12 cuts. So just be writing the initial burning point of the cuts, and it's going to transfer everything. Then it should have been. So I'm going to do this. I'm going to skip the video just to not waste. Okay, let me just Control V. So that's how you add all the initial boiling point, and it's going to make it to be the final boiling point of the next course. Okay, so of the previous course, I mean. So I'm done. So we move from here. So I've copied all the values to the list in there. So once you're done with that, you click OK. You're going to create the assay from the course. So you have the data. You can copy the data here. So the first thing that I'll do is the pure components data that I'm going to copy from there. So we have the pure component from ethane. From you can see it's a mass basis, so you copy these values and paste it into Aspen HYSYS from ethane here. See, I'm not sure if this data and pentane. So we still need to add we still need to add a lot of data here. We need to add propane, isobutane, and everything. Ethane, propane, isobutane, normal butane. Let me check. So we need to add pentane and normal pentane. So I'm going to do that. Paraffin. C5, I want to pick C5 paraffin. Yes. Add this. C5, so pick C5 paraffin again. So normal pentane, add it to. So I'll copy their fraction now. put it there. So, okay, in this in by mass percent on some weight percent. So the next thing is distillation data. You can add for the oil crude, because I have the oil crude distillation data based on 2 boiling points. So 2 boiling points of the oil crude weighs on. So I'm going to weigh. Okay, this will be the final boiling point of the crude of the cut. So I'm going to add it here. Oops, supposed to add it here. So I need to add some data that is you need to add. The listing that is provided is not enough, so we have this. So the pure comment. Next thing is this cut seed. So for the cut seed, there are some things that I need to insert here, because the values there is 0 0. There is no value for this place, so I'm just going to, let me just say put it here. There's a mismatch over here, so I'm going to copy it here. I'm going to start from here, because this value is from here. You just put where you have the values and leave where you don't have the values. So then I'll copy for the oil crude. Yeah, this is the bulk properties of the oil crude. Oops. Yeah, I'll change the units later. So we have the units. The units here, pounds per feet cube. So I'm going to change it to pounds here. Okay, let's change the unit here. Double click on it and change the unit here. Okay. Oops. Yeah, it's changing units because it's automatic. So I'm going to copy it back. Was okay. So this, go to paste this one back. So with this, I can characterize the assay. So I'll call this. I'll change the name. I want to change the name of the assay here. Okay. Heavy Crude. So I'm going to call it Heavy Crude. So that's arranged it based on. You can see from source imported file, user specified data. So I'm going to change. This is not important. This just all this to classify the assay. Like if you want to write reports on it. So I think I can classify this assay. Okay, the characterization has been done and there's result for it, and you can check the result and the message cut width does not add up to 100. So I think it's going to normalize the cut sheet as a description, and which percent is 550. I think maybe I made a mistake here. So I will characterize the Basra so that it will be able to use it in the simulation. So I'll characterize this one too. Okay, so let's check the cut sheet. Specify for this. This is distillation to one. There's no cut sheet specified for this. We just using it. Based on initial point paint and all this kind of thing. So we have the 2 boiling point data, and this is the information given region or something. So although my data feed might not be as accurate as the one from the standard website, but I'll just be blending the crudes and be seeing, comparing my result in the simulation. So everything that you need to do in the properties environment has been done, since you have characterized the crude oil and you have added all the data that you have for the user defined crude oil. So I'll go to the simulation environment. You don't need to define reaction, because no reaction, we are just doing refining simulation. Okay, this is my simulation environment. So in the simulation environment, it's just I've already set up the block in order to reduce the time that I'm going to be using to do this video. So I will explain the block now. So in the block we have the oil feeder, which is the unit operation that we use in Aspen HYSYS for blending crude oil that we define in Petroleum Assay. So I'm going to be blending the crude oil inside the oil feeder. Then from the oil feeder we have the puriter, which is for creating the crude to the distillation column entry temperature. So it can be an heat exchanger in the plant or something. So I'm using a heater to just to model it in my system, in my simulation now. So we have the one crude. So we have the desalter, which is like a two-phase separator for desalting, like removing salts from the crude oil. So you use water to salt it, at the temperature. So I'm using a mixer now just to simplify the process. So we have another heater, another preheater. Then we have the Atmos heater, that is the fire heater for the last heater, or fire heater for the crude, in order to set the crude to the column entry temperature. You understand? So from there we have the atmospheric distillation column. The atmospheric distillation column is where the crude is fractionated into different components like diesel, kerosene, HVGO, atmospheric gas oil, naphtha, you understand, and the rest. So from the atmospheric column we have the atmos condenser, which is condenser duty, because the atmospheric column is, let me open it so that I can show you. Okay, although I've already defined the input expirat, and I'm not using it. I'm just writing the topography of this distillation based on this street, on this table here. Yes, and so it is a reflux absorber column. That is, we are having only condenser, we don't have a reboiler in the column. So that's why you're having the P bottom here to be empty. So for the condenser, the distillate is in liquid form, it's nothing. So it's a total condenser. And we're having a water draw from the condenser, which is this where is this water draw? Atmos overhead water. So that's the water is from the condenser, and which is the condenser. The naphtha is actually taken from the liquid distillate from the condenser, and we have the atmos residues for the bottom of the tower. So from here you're having like your atmos residue is 50 main tower. That is the number of stage in this column is 50 stages or tray. So you can see the number of trays is 50 tray, and you have other units auxiliary unit operation attached to the column. I will be explaining that later. So from there you have three side stream that is taken from stripper H. So we have the kerosene side strip, we have the diesel side strip, we have the HVGO side strip stripper, and going to the unit of side operation. So from the, like I said, we have like three sides side drop, like liquid drop, liquid product drop from the column, which is taken from three side stripper, and those side stripper, they are steam strip side stripper, so like a reboil absorber to your sun. So you use a stream to strip off the light component from the side draw from the column. Yes, and so from this kerosene stripper is coming from the liquid draw is taken from stage 10, and the vapor that is stripped away is taken back to stage 6, and this is following the same process 20 to 16, and HVGO 30 to 26. And we don't have rectifier, we have pump parents too, which is based on the side strippers configuration, but this is from 10 to 7, and this is from 20 to 17. So you take the liquid draw from 10 and you pump it back to stage 17. It's an HVGO, you take the liquid draw from stage 13 and pump it down to stage 27. Yes, and so I'm going to be making spec for this. These are just like I just made the simulation in order to make it simple to explain and to cut short this video. So the others we are going to be explaining in the next video. So because I'm going to be stopping this video here. So I'm going to start doing the simulation. So the first thing I'm going to do is adding the crude. So I'm going to pick all the crude assay that I want to use. So I'm going to be using also, I'm going to be picking it one after the other. So you can see the block has light up once I started picking up the crude instance. So you can add a fill stream to blend with the crude anything that you want. The component is already defined. So this is where you do the blending in the parameter tab of the unit of the feeder, oil feeder unit operation. Yes, petroleum feeder, that's the main name. The name that I gave to it is oil feeder. Yes, and so we have the Bonny Light is going to be having fraction of 0.3. Let me use 0.3 later. You just complete like the fraction of the Bonny Light in that blend is going to be 0.3 mole fraction. So because the balance type is in mole, so it's going to be mole ratio of 0.3. While the Basra, I want it to be 0.2. Because of my characterization, I want most of my crude to be so the last one will be calculated, you understand, so that all the fraction is 1. So this will be the initial boiling point, this will be the final boiling point of the crude, and everything is set here. For my own crude, you can see is having high final high crude, is a heavy crude, you understand. So the blending is just there. So in Fahrenheit, so the worksheet, you can see from the worksheet. So this is the crude that is coming out, crude oil stream that is coming out. So I will flash this stream based on the thermodynamic condition. So the temperature of the crude is 100 Fahrenheit. So I'm going to write 100 Fahrenheit. The pressure is 300 psig. I think it's pounds per square inches. I don't know the meaning of the G. So we have the flow is in standard liquid flow, volumetric flow in barrel per day, which is 101,000. That is 100,000 barrel per day. So you don't need to do the composition. You can see it has even given me the OK status because the composition has already been given based on the characterization and the blending, you understand. So you remember in the oil manager, you are the one that will install the oil in the flow sheet, but this you can use this feeder to do the oil installation, and also the oil has been set here. So for this preheater, I'm just going to flash it out from the worksheet here. So the outlet temperature from the preheater is, actually I'm following this this is the distillation column. Okay, this is the second one. So I'm following this crude simulation analysis manual. So I'm going to be using their parameters like simulation parameters to do my own. But if there is a need to adjust them, because I'm not using the same crude that they are using, I'm trying to use another different crude to do this simulation and check the results that I can get. You understand? So I'm going to be, this is the specification for that crude oil, you understand. So I'm going to be using the preheater outlet stream is 260 Fahrenheit and 294 psig. So I'm going to be specifying it here. So okay, so this one is 260 Fahrenheit, okay, I'm writing 290, 260 Fahrenheit and 294. This one is, there is a period drop of 6 or something, 294. There's a period drop of 6 psig in this stream. You can check the period drop from parameters here. Okay, is in this one is in kilopascal, is calculating period drop in kilopascal, because that's the unit. So this block has been done. So the next thing is to specify the water flow, because they are giving us the water flow to be 500 barrel per day of water. Then the outlet temperature from the desalter. With the help of our HYSYS configuration, you can do this. So I'll tell you how to do that. So you just do the water flow first, to do the composition for water, so that everything is one. So once you pick the composition, the next thing is to normalize the order to be equal to 1. So because you have already picked everything to be 1, more fraction, volume fraction, although I'm using volume fractions, you understand. So the order is going to be having 0 volume fraction. So you have normalized it. So then the barrel pool, you put 500. Don't need to flash the flow and the pressure, just leave it. So to do that, you have to use something that we call equalized pressure in a mixer. It's going to equalize all the pressure of the connecting stream to this mixer, because most time in reality, like any junction or any T, the pressure of that junction of the stream must be equal. So I'm going to pick equalize all here. So once I'm done, so I'll go to the worksheet, then I'll flash the outlets the way I want it to be. So we have the desalter, one wet scoop. So I'll flash this one to be having the temperature and the pressure that they want this. So it's having 260, 260. Although the pressure has been flashed based on the equalizer, it's going to be having the inlet pressure. So I'm going to flash the temperature to be 260 Fahrenheit. So it will calculate the temperature of water that I need. Okay. So I'm going to have 260. Don't know why I'm writing wrong. 260. Okay. So it has calculated the temperature of the water that it needs 395.8 Fahrenheit of shelter water. So that place has been done too. So we go to the second heater. So for the second heater, we have 450 and 260. There is a period up to, so 450 Fahrenheit and 260. Okay, let me check it again. 260 psig. I'm going to flash it. 450, 450 and 260 psig. So it has flashed the stream and calculated the duty that is needed in the cooler. So the next thing is the column. So going to the column, we are going to do the feed preparation, because like I said, it's a reflux absorber, so we have direct fire heat. So the feed location, you have the feed heater is 10 years, there is going to be outlet of the feed there is going to be 25 psig and 635 Fahrenheit. There is between, this is the inlet crude column inlet temperature. So the temperature of the crude must reach this temperature before it enters the crude column. So we have 635 Fahrenheit here. So I'm going to be specifying that to be 635. See, 635, and I'm checking I think forgotten the temperature, the pressure. So the pressure is, where's the pressure? 25 psig. 25. So it will flash and calculate the duty, and it will flash. So okay, once that is done, so we go to the okay, before I enter the column, let me set all the outlet stream, because before you can define a unit operation outlet, it's best to define all the inlet stream to that unit. That's the only way you can solve it. So I'm going to define all the stream that we are using. So I'm going to specify them. So from the column, it is given that we have this stream is from the side stripper. So we have the stripping strip for each side stripper, for the kero side stripper and the diesel side stripper and the HVGO side stripper. So for the kero side stripper, we have the stripping strip to be having 2,500 pounds per hour, and that's 500 Fahrenheit and 150 psig. The stripping stream should contain only water, so I'm going to be starting with the kero stream here. So I'm going to be writing the composition and doing this thing over and over again. So okay, you can write mass fraction here to be 1 normalized. So I'm just going to do for the keros, then skip the video for the others and show you once I'm done. So okay, it's 2005 pounds per hour. So let me write 2500 pounds per hour. So okay, the temperature is already kind of 500, 150. 500, 150. Okay, so I'll flash the kero stream. So I'll do for the rest. So I've done for all the style stripper stream, because they're having the same value and they're having the same values and temperature and pressure, the same flow rate, 2005 pounds per hour. So for the outmost stream, that is the main stream of the distillation column, they're having the same composition. It is water. So okay, we're having 1 year. normalize to others to 0. So this same temperature 500, oopsie, 500 and 150 psig, but the flow is 20,000 pounds per hour, so more flow here. So that's flash for the mainstream here. So you can check for the mainstream. We have the, where's the mainstream? Feed location crude oil 340, while the stripping stream at the bottom 20,500 and psig. So that's all the inlet stream to the column, and you can see the the feed location here 40, while the stream is 50 here. So the next thing after doing the inlet stream is to do the pressure network of the stream. You can see from the pressure is giving us that the pressure of the condenser is 4 psig, while the top tray is 12 and the bottom tray is 22 psig. That is, the pressure increases down the column. We should expect pressure to increase with depth. Yes, and so you can do the pressure profile here, but there are some settings that you have to remove, like data P, or this data P something. So because problem too. I say the pressure top is, or pressure of the top is, what's the pressure? I've forgotten. 12. That is pressure from the condenser is pressure drop for the condenser is around, I don't know if you consider that. So pressure at the bottom is, okay, pressure, I'm picking the right thing. Pressure at the bottom is 22. So it will set most of it there. Okay. Okay, this one is 12 here. Okay, so it has set most of the pressure profile based on interpolation. So the condenser pressure is 6, I think is forgotten again, 4. So the condenser pressure is 4. So the pressure from the condenser is for 8. No, it's not 8. Yeah, it's 8. So the pressure from the condenser is 8. So the next thing is to do the efficiency, because they are saying something there that the stage efficiency is it's not 100%, so it's not theoretical, you understand. So they want to use race stage in the simulation of the process. So you go to efficiency here to specify the efficiency. So you can, because there are a lot of stages to specify efficiency, I don't want to make mistakes, so I'm going to group them. So grouping them is easier to do. So I'm going to be grouping them based on 6 group. The one that is easier to, that is more challenging, they're going to be in group 0, so that I won't be changing them, just to work very fast. So I've grouped them based on 6. So because this is condensed and it must have efficiency of 1, so it's not going to be in group, 0. So it's going to be in another group, but I'll change that out later. So the first group is going to be based on this, the one that is having 1 3 40. So the first group will be this will be group 1, why the one that's having 30, because most of these size repairs also having 30 efficiency, you understand. So those one that's having 30, I'm going to make them to be group 0. So this will be group 1 2 3 4 5 6, you understand. No, group 1 2 3 4 5, this will be group 0, you understand. So I'm going to start doing it now. So from here to be, this from first column to 6th column. So I'm going to do it and skip the video. So 6th column is here, so this will be group 1. So change all this one to 6th column. So from 7 to 10, that's group 2. 7 to 10, group 2. change this one to group 2. So I'll just be changing the values later when I'm skipping the video. So we have from 11 to 17 group 3, 11 to 17 group 3, from group 11 to group 17 group 3. So from this group 16 mistake, 11 to, so this will be group 4, 17 to 30 will be group 4, 17 to 30 4. So because 31 to 39 they are 30% efficiency, that's 0.3, so it's going to be group 3, group 0, sorry. So 340 will be group 5, different efficiency. So I'm trying to make 340 to be group 5, and condenser is also having group 5 because they are also having 1 1. So I'll just change all this one that is having this one that I need to change to group 1. I'll just be doing that to group 1 just because I didn't miss it and skip the fee. Okay, it's all done. So I have added the group. So 1 1 1, just added the internals on the internal ones. So the others will be group 17. So I'm done with this. So once I've done this, the next thing is to make group, this one will be 0.3 because it's 30% efficiency, while group 1 is 80%, that is tray 1 to tray 60, 80% efficiency. So I'm going to making it 0.8. You see that the efficiency will change in the input. You can see it's changing in some based on my grouping. So this will be 0.5, 0.5. So by this will be 0.7, 0.7, and this one will be 0.5 again, because I'm supposed to lump the group 2 and group 4 together, but it's just to make things easier. So 0.5 again from 17 to 30. So you see 17 to 30 to be 0.5. So we have 17 over here to 30, group 30 0.5, where the rest will be 0.3. You can see group 40 is 1. You understand? So that's it. So we are done with this. So the next thing is to add spec, because most of the thing that is needed for this has been done. So you can do the spec on the monitor page. There are some spec that has already been added, although I remove most of the spec because it is a complex column and you have to just know what you are doing. You understand? There's a lot of variables to play with. You understand? But HYSYS actually solve this column based on mesh and mesh equation, and it has to solve the there'll be some specification, you understand, in order to solve the equation, because the equation is not squared. You understand? So you have to put some specification to solve the variables. So add the reflux ratio, distillate rate, reflux rate, the bottom rate. You understand? So there are some spec that is given in this, and because there are some distillate product purity. This one is for distillate analysis, like it's going to be doing D86, like it's the move at this move fraction, fourth fraction. It must have this temperature, that is the normal boiling point of 410 Fahrenheit. So, and they are saying the distillate rate is 30.20 barrel per day approximate. So I'm going to be putting these values there and trying to put this purity product or specs on the simulation. You understand? I'm trying to get to it, and all these pump around values I have to put it in the simulation in order to get a value for the column. So I'm going to be doing that now. So we have the distillate rate to be what they call it. Forgotten again. So we have distillate rate to be 20 30,200 power per day. So I'm going to change this rate to be, I'm going to edit this text to be volumetric, standard edit volumetric. So as 30,200, I know that's the SI unit. So I've added this spec, you know. So the next thing is to add the purity spec. So we call it cut point in Aspen HYSYS. So once you add the cut point, you have the ASTM. There's different kind of purity. There are two boiling points, you understand. So it's just based on the distillation curve. So you, because the condenser is from the condenser, and anything that is coming out any unit operation, we have the same composition, the same values. That is, any stream that is coming out of any container or vessel should have the same temperature of that vessel. You understand? That's just the idea. You understand? So we have column condenser here. We have the type. So instead of picking the stream, I'm just picking the unit from operation that the stream is coming from. So this is the vapor fraction liquid phase. So the cut point is 95 specified. So I'm going to specify it 410 here. So I'm going to change this one to naphtha, something like naphtha cut point. I'll add something to the front one. Okay, let me copy this because I want to make my work easier and faster. So we have this. So I've done the, so you can do any all this, you can use all this API for DA86 conversion type just to convert to true boiling points and all this kind of thing and all this scrapping stuff. So I've done that. So this is the spec here. I think it's now estimating it. Okay, let's just leave it like that. So I'm going to add other spec, other purity spec for the HGO product, diesel product, and the kerosene product. So, but I'm going to, it's just following the same process. So I'm going to do for the kerosene and skip for the rest. So to do for the kerosene, you add this spec again, cut point 2. So it's, I'll copy it here. So I'm going to call this, edit this way. I'll be able to use the name again. So I'm going to call it cut point. So it's going to be coming from kero stage, the bottom stage of the kero size stripper. So we have the last stage of the kero size stripper, which is 10. So the same fraction 95, and I'm going to be giving the values there. So the values in this place for the kero is 525 Fahrenheit. So I'm going to be writing 525 here, 525 Fahrenheit. So that's it. So I'm going to, so I've added the cuts for the kero, diesel, and HGO cut point. So, and the next thing is to specify the product flow of the kerosene and the diesel and the HGO. So like we have done for the naphtha stream. So I'm using this. So I'm going to be specifying the product flow. So the product flow is for the kero is 8,800 barrel per day. So I'm going to do for one and skip for the others. So you just change this to standard. So okay, 8,800 barrel per day. So let me just check. Okay, that's it. So you, then you make it a spec. So let me just do it first and do it for the second. Okay. So that has been done. So the next thing is for the pump around, to give specification for the pump around, because those pump around we need specification to solve to. They are adding degree of freedom to the column as you're adding them to the column. So I'm going to be using the data that you have there. So for the pump around, we have two spec, the flow and the temperature spec. So I'm going to be adding the flow and this temperature for the first one is 25,000 barrel per day flow, and the return temperature to be 200 Fahrenheit. So I'm going to be adding, okay, the rate, that will be the way I'm going to be adding the flow. So I'm going to change this to standard rate. So we say 24,500. Let me check again. 25,000. Okay. 23, 25,000. So for the temperature, so I'm going to do the temperature. So I'm going to change this to return temperature, and for the pump around spec, the return temperature is 200 Fahrenheit. Alright, so 200. So for the second, let me skip second one. Okay, this has been done too. Let me check the there is any specification that we can still add. Temperature. Okay, I think temperature actually help for convergence more. So I'm going to be, let me add this top shade temperature and the bottom temperature here. So you do the same thing, add spec. Okay, should have done it before here. Yeah. Temperature, column temperature. Okay, so specify to be first stage. So let me check the value, 250 Fahrenheit and 650 Fahrenheit. Change this name to top temperature. Okay, 250 Fahrenheit. Oh, okay, it's not running. So let me move down so that it will not run, because sometimes just run very fast. Temperature. Bottom temperature. Start with calculator. Okay. Last stage 50, 650. Yes, 650. Let me check the value again. Yeah, 650. So done. So to know the spec to choose, most of these, because I'm using different crude, and these cut points we will actually it's just the distillation cut point of the product specification. So I'm not going to be using this spec first, because I want to be characterizing the crude based on the fixed operation parameter for the column. I'm going to be doing a fixed operation parameter, like is the pump balance, you're going to be having a fixed rate, the temperature and everything, you understand, and the reflux ratio, the distillate rate, you understand. So I'm going to start from there. So the spec that I'm going to specify is based on the operation, not the product's purity or something, or the temperature. So let me remove all these temperature specifications. So I'm going to specify this. I'm trying to run. Okay, it has, all the specification has been gotten. So okay, let me put this to be 0.2 and change the spec. Maybe it's some technical. Okay, so it has converged. Okay, I can now, because it's based on calculation, like the reflux ratio is very easy, and maybe the estimate that is using is not good, so I have to make it worth it to the value. So I'm going to be fixing the flow now. So it has converted to the new specification and reduced the reflux ratio to 0.1892. So that's it. And you can see from here we are having 467 naphtha. That the naphtha is having a higher boiling point, which is not light enough. So we have nickel cut points and everything. So all these things can be adjusted based on the feed composition that we are sending out, that we are blending. So I'm going to be blending the feed and checking the result, and you can see the result, it has converged. So from my blender here, I'm going to be changing some blending ratio that we are using. So go to parameters. So I'm going to be deleting first, so that's not great, not because HYSYS calculation is automatic. So I'm going to be boiling this one to be 0.1. I don't want it to be more than, so this Basra is 0.6. I want more light crude so that I can get more naphtha curve to just converge automatic. based on the operation. So let me check the cut point on the monitor. It has reduced 552, so you can see it has reduced. So that's how you reduce it a little bit, or you change the operation condition. So I'm going to change this one to 0.7, and I'm going to try and change this one 0.05 so as to reduce the heavy components that we have. It has converged again. I'm checking it from this trace window here and check the results, and we have the monitor. You have 4.4. You can see 4.45. So that's how you reduce it much. But I can always go by this because we are using Heavy Crude and I'm just using different. I have to be changing the parameters in another video. So I think I will end this video so as not to spend a lot of time on this video. I'm going to end it now. So you can see the performance here and the flow and the plots of the column, and you can see the boiling point curve. You can change the properties to reduce to boiling point on condenser on condenser here, and the stripper here, and the HVGO stage 10. Here's the kerosene stage 10, molar 15 points for the liquid, light liquid phase. Not showing. Oh, I didn't select the one that I want. Okay, so we have, I actually select something. So true boiling point data. Okay, can change all this data here. So these are the boiling point curve for the stream and the molecular and the flows and everything. You can check it there. You can check the flow sheet. You can check the summary of the flow and the composition here. We have the kero stream and the composition of these 350 to 590 cut points from the composition and everything. So that's that on the first video on this series. So in the next video we are going to continue from here, going into the Debutanizer and the vacuum column. So I'm going to be teaching you guys how to do vacuum distillation column and the Debutanizer column. So thank you for watching. Stay tuned to this channel. If there is anything that we want us to discuss on this topic, you can always drop a comment or a review, and you can check us on our website www.nubera.com. So have a nice day.